Welcome to our journey into organic chemistry. Today, we are going to explore a fascinating topic called racemic mixtures and resolution. Have you ever wondered why two molecules that look almost exactly the same can behave in completely different ways? By the end of this video, you will understand exactly how this works and why it is so crucial for modern science. Now that we know our topic, let us start with a simple analogy. Imagine you work in a shoe factory and a machine accidentally dumps thousands of left and right shoes into a giant bin. If you pull one out at random, you have an equal chance of getting either. In chemistry, molecules can also have left-handed and right-handed versions called enantiomers. They are perfect mirror images but cannot be stacked perfectly on top of each other. When a reaction creates an exactly equal number of both, we call this perfectly balanced blend a racemic mixture. This brings us to a very interesting property of these mixtures. Why does this perfectly balanced blend behave differently than a pure batch? It all comes down to optical activity, which is the ability of a chiral molecule to twist a beam of light. The right-handed molecules twist the light to the right, and the left-handed molecules twist it to the left by the exact same amount. Because a racemic mixture has an exactly equal number of both, these twists cancel each other out completely. The two opposite molecules fight to a perfect tie, making the mixture optically inactive. To truly understand this cancellation, let us look at the mathematical formula for the specific rotation of a mixture. This formula comes from the idea that the total rotation is just the sum of the individual rotations contributed by each part. In this equation, alpha sub m represents the total observed specific rotation of the mixture. The symbol F sub plus is the fraction of the right-handed, positive rotating enantiomer, and alpha sub plus is its specific rotation. Similarly, F sub minus and alpha sub minus represent the fraction and rotation of the left-handed enantiomer. If the fraction of either enantiomer increases, the total rotation will shift in that direction. Before we can prove why a racemic mixture has zero rotation, we need one more piece of the puzzle. This equation states a fundamental rule of nature regarding chiral molecules. The left-handed version of a molecule rotates light by the exact same amount as the right-handed version, but in the perfectly opposite direction. The negative sign in the formula indicates this opposite direction. For example, if the right-handed molecule twists light by positive 10 degrees, the left-handed molecule will twist it by negative 10 degrees. This perfect symmetry is what makes the math work out so beautifully. Now that we have our formulas, let us prove mathematically why a racemic mixture is completely optically inactive. We are setting out to calculate the total rotation for a perfectly balanced mixture. Because a racemic mixture is an equimolar mixture, meaning a perfectly even split, both the positive fraction and the negative fraction are exactly 0.5. We start by substituting these fractions into our main equation for the specific rotation of the mixture. Next, we apply the opposite rotation rule, replacing the left-handed rotation with the negative of the right-handed rotation. This shows that half the mixture is trying to rotate light one way and the other half the exact opposite way. Continuing with our derivation, we can now see the final result taking shape. We have a positive term and an identical negative term in our equation. When we add them together, the positive and negative terms perfectly cancel each other out. This leaves us with a final rotation of exactly 0. This mathematically proves our earlier concept. Even though the mixture is full of molecules that individually have the power to rotate light, their perfectly balanced opposite effects result in complete optical inactivity. This is a beautiful example of how physical symmetry translates directly into mathematical cancellation, giving us a final result of 0. So, we have proven that a perfect racemic mixture has zero rotation. But what if the mixture is not perfectly balanced? To figure that out, we use the formula for enantiomeric excess. This formula tells us conceptually how much more of one enantiomer we have compared to the other. The symbol E stands for enantiomeric excess as a percentage. The term alpha sub O is the rotation we actually observed in the lab. The term alpha sub P is the known rotation of the pure right-handed molecule. If the observed rotation matches the pure rotation, the excess is 100%. If it is 0, the excess is 0. Once we know the enantiomeric excess, we need to find the total percentage of that specific enantiomer in the entire mixture. This formula conceptually breaks the mixture into two parts, the pure excess part and the remaining perfectly balanced racemic part. The symbol P sub plus represents the total percentage of the right-handed molecule. We take the excess, E, and add half of the remaining racemic portion, which is 100 minus E. We divide by 2 because that remaining racemic part is split equally between right and left. As the excess increases, the total percentage naturally increases as well. Let us see these formulas in action with a concrete example. A student synthesizes a chiral alcohol. We are given that the pure right-handed enantiomer has a specific rotation of positive 13.5 degrees. The student measures their mixture and observes a rotation of positive 2.7 degrees. We are asked to find the exact percentages of both enantiomers. We choose the enantiomeric excess formula first to find out what fraction of the maximum possible rotation we actually achieved. We plug in positive 2.7 for the observed rotation and positive 13.5 for the pure rotation. Continuing with our calculation, we found a 20% excess of the right-handed enantiomer. This means 20% is pure right-handed and the remaining 80% is a balanced racemic mixture. Now we use our total percentage formula. We take the 20% excess and add half of the remaining 80%. 20 plus 40 gives us 60% for the right-handed molecule. Since the total must be 100%, the left-handed molecule makes up the remaining 40%. Physically, this means the mixture is slightly biased toward the right-handed shape, which is exactly why it still rotates light slightly to the right. Now that we can calculate what is in a mixture, how do we actually separate it? Imagine trying to sort that giant bin of mixed left and right shoes by weighing them or measuring their length. You will fail because a left shoe and a right shoe weigh exactly the same. In chemistry, enantiomers have identical boiling points, melting points, and densities. We cannot separate them using normal physical methods like simple distillation. To tell them apart, you need another object that also has a handedness. Just like your own right foot fits perfectly in a right shoe but feels terrible in a left shoe. This brings us to the chemical process called resolution, which is how we separate a racemic mixture into its pure enantiomers. Because direct physical separation fails, chemists introduce a pure single enantiomer of another chiral compound, known as a resolving agent. This reaction converts the two mirror image enantiomers into a new pair of molecules called distereomers. Distereomers are stereoisomers that are not mirror images of each other. Because they are not mirror images, they have completely different physical properties, like different solubilities. We temporarily attach this helper molecule to make them look different, separate them, and then take the helper off. Let us look at a visual flowchart of this entire resolution process. At the top, we start with our racemic mixture, a 50-50 split of R and S enantiomers. Notice how we add a pure chiral resolving agent, labeled as R agent. Following the arrows down, this creates two distinct diastereomers. Because these new molecules have different physical properties, the flowchart shows them being physically separated into two different branches, often by fractional crystallization. Finally, at the bottom, the resolving agent is chemically removed from both branches, leaving us with the pure isolated R enantiomer on one side and the pure S enantiomer on the other. Let us apply this resolution concept to a real chemical example. A chemist has a racemic mixture of a chiral carboxylic acid and needs to isolate the pure right-handed acid. We are given equal amounts of right-handed and left-handed acid, and we will use a pure right-handed amine base as our resolving agent. The strategy here is a simple acid-base reaction. The racemic acid reacts with the pure right-handed amine to form a mixture of two different salts. As shown in the chemical equation, the right-handed base forms an ionic bond with both the right-handed acid and the left-handed acid, creating our two diastereomers. Continuing with our resolution example, we now have two distinct salts. One is made of two right-handed parts and the other is made of a left-handed and a right-handed part. This is the crucial step. Because these two salts are diastereomers and no longer mirror images, their physical properties are different. Specifically, their solubilities in a solvent are not equal. This mathematical inequality highlights that difference. Because of this difference in solubility, one salt will dissolve easily in the solvent while the other will form solid crystals. We can now easily separate them by filtering out the solid crystals. For the final step of our resolution, we take the solid crystals of the right salt that we just filtered out. We treat this salt with a strong acid represented by HX. The strong acid breaks the ionic bond, grabbing onto the base and releasing our desired pure right-handed acid. The chemical equation shows this final recovery step. The pure acid can now be extracted, successfully completing the resolution process. Physically, we have used a temporary helper to sort the molecules and then removed the helper to get exactly the pure enantiomer we wanted. Why do we go through all this trouble to resolve racemic mixtures? These concepts are absolutely critical in the pharmaceutical industry and modern medicine. Many drugs are synthesized in the lab as racemic mixtures, but the human body is a highly chiral environment full of handed proteins and enzymes. Often only one enantiomer provides the medical cure, while the other might be inactive or highly toxic. For example, the drug thalidomide was sold as a racemic mixture. One enantiomer cured morning sickness, but the other caused severe birth defects. Today, regulatory agencies strictly require testing both enantiomers separately to ensure safety. Let us review the key takeaways from our journey today. First, a racemic mixture is a perfectly balanced blend of two mirror image molecules, which makes it optically inactive. Second, because enantiomers have identical physical properties, they cannot be separated by simple physical means. Finally, resolution is the clever chemical trick of temporarily attaching a handed helper molecule to turn them into diastereomers, which can be easily separated. You have now mastered the basic concepts of racemic mixtures and resolution, a crucial skill for creating safe, targeted chemicals in medicine. Great job!